Okay, so we have this driven at this frequency. Let's say that we increase the frequency. What's going to happen? So let's say that we have omega go to 500 radians per second. And now the reactants are both going to change, and so the impedance is going to change as well. So yeah, the impedance, it looks like a constant, but that's only for a given frequency. And so again, these reactants, these kind of act like resistors, but they depend on the frequency that you're trying to drive them. And the inductor, maybe it's not too surprising that if you try to drive it at a high frequency, you're going to get a much larger inductive resistance or reactance, but effectively it acts like a resistance. And that's because the inductor is trying to oppose any change in current. So if we increase omega, the inductor is not going to like that. Capacitor, though, is going to be happy. If we increase that, the capacitive reactance is going to drop. And so like right now, this is a capacitive type of circuit. But if we increase the frequency, we'll have to see what happens. And we can increase it to, it depends on how much you change it. But we could get to the point where it flips to where the inductor is more significant than the capacitor. So let's just change it to 500 radians per second. And let's call these Xi-L prime and Xi-C prime. And I don't do this often, but let's not go through the formality of units because we're literally just recalculating something. So we throw on the exact same conversion factors. So I'll be lazy about units for once. Don't do it often, but here we have, let's call this omega prime. So we have 500 radians per second times 47 millihenries. So that's going to be 23.5 ohms. 500 over 1,000 is 1/2. Half of 47 is 23.5. So you can see that the inductive reactance increased. We're trying, the power supply is working faster. It's trying to change the current more rapidly, and the inductor is saying no to that. It's going to resist that more. Now the capacitor will be happy with the situation. 1 over omega, and then we have 66.7 microfarads, so we 10 to the 6. So let's calculate this. So I'm getting about 30 now. That capacitor is still in. But you can see that the frequency plays a very big role in how these circuit elements are going to react. We can find the impedance as well. And again, that would be 19.9 squared. And then we subtract these, let's call this Z prime. So I can do 30 minus 23.5 because we're going to square it. Positive or negative doesn't matter here. So let's see, that's 6.5 squared. So 42.3 roughly. And that would be in ohms. So the impedance will change as well. So I'm going to take the square root of 438.3. So now I'm getting 20.9 ohms. So before we had 35.7 ohms. was kind of like the effective resistance of this circuit, if we're talking about like peak values. So let's look at the peak current now. So remember, the peak current is the peak EMF, which has not changed. But now the inductance has decreased. Or the effective resistance of the circuit has decreased now. So we do 125 divided by 20.9. This is 5.98. Let's just say this is 6 amps. So again, same power supply. We still have 125 volts, but now at a different frequency, we're getting a significantly higher current. And so the current depends, the circuit will respond differently to different frequencies. The current in this case increased. Now, let's say our goal is to find the frequency that will maximize the current. Or I should say maximize the peak current. Any idea how we could do that? Don't want to, or maybe if you read ahead, if you read the book, you should know this, but let's say our goal is to maximize the peak current. What condition should we set up so that that would happen? I'm going to write down the condition. So before writing it down, let's look at the peak current is going to be the peak voltage divided by the impedance. So if we want to maximize, like this is fixed. We can't do anything about the voltage here. Should have been EM the whole time. But we can change the impedance by changing the frequency. So the goal is to maximize the impedance. Well, we want the peak current. So our goal is to minimize Z. Minimize the impedance. By making Z as small as possible, we'll get the highest current for a given input voltage. And so how do we minimize Z? Well, Z has, we're adding two things that are always going to be positive. Well, never negative, anyways. So we take R squared. R is fixed. It doesn't care about the frequency. And then we're adding something else to it. And so the condition to minimize the impedance is set these reactants equal to each other. The inductive reactance equals the capacitive reactance. Because if these two are equal, then we're just going to have Z equals R. ZL minus IC is going to be 0. So Z is the square root of R squared, or R. And if this condition does not exist, if these are different from each other, then when we square it, we're always going to get a positive value. And so that'll make Z bigger. So if we want to minimize Z, we have to have this condition. So we have omega L. You may have seen this before. 1 over omega C. or omega squared equals 1 over LC. That'll be the angular frequency that gives us the largest peak current for this particular circuit. Like RL and C are fixed. EM is fixed. The only thing we can change is omega, and this will give us the largest peak current. So let's just do one more thing. Let's calculate. Let's call this omega naught. That's a frequency that will maximize the peak current. Okay, so omega naught squared. So L is 47 millihenries. And then the capacitance it's microfarad, so we put a 10 to the 6 on top. And a coulomb times a farad. Wait, I wrote that wrong. A coulomb equals a farad times a volt. So, and an amp times a second is a coulomb. So here, let's look at our units. We have henries, amps, farads, volts, and coulombs. On bottom, we have henries, farads, volts, seconds, coulombs, amps, and seconds. So we get inverse seconds squared, then we take the square root, we'll have inverse seconds or radians per second. So let's multiply these numbers on the bottom. We have 10 to the 9th divided by 31/35. That would be in seconds squared. So let's see. I'm going to write this as 10 to the 5th times 10 to the 4th. Let's do it like that. And again, I'm just doing it this way because I want an even exponent here to take the square root. So I can do 10 to the 5th over 31/35. So I'm getting 31.9. That's, and then if we take the square root of that, then the square root of 10 to the 4th is 100. Square root of a second, square root of the second. So I'm just going to take the square root of 31.9 and then multiply by 100. So this is omega naught would be 565 radians per second. That would give us the largest peak current for this, for given, well, regardless of the voltage, but yeah, for these values of the resistance, the inductance, and the capacitance, driving it at that angular frequency would maximize the current. All right. So any questions on these RLC circuits? Now, you might be wondering, what about this phase here, 5? Who cares about that? Actually, let me stop recording for now.